I've got last round is to show that count the number of independent parameters in the solution of the vector equation, then we found that they were D in D dimension. They were D parameters parameterizing the vector in U. And we had an antisymmetric rank 2 tensor, or antisymmetric D by D matrix, which had a half D times D minus 1 independent numbers that goes into it. So if I add the two up, I find that there are half D times D plus 1 independent parameters parameterizing any solution of a Killing vector equation in D dimensions. This is exactly the number of generators that we expect for the Lie algebra of the corresponding D. So there are half D times D plus 1 generators of the Lie algebra the array. Let's look at the counting exercise. It's the solving the Killing vector equation, and then working out how many numbers, how many parameters I needed to specify the solution. Okay. But I didn't tell you what those generators were, like on the representation of the generators. And that's what I want to do today. So how do we determine the generators of the Lie? So this starts with the following observation. We start by making an infinitesimal transformation. So x nu goes to x nu plus small delta x nu. And now we know the form of the delta x nu. This will take the form a nu plus figure nu nu x nu. Then I compare this to the form x nu plus delta x nu that I know because any Poincare transformation is made up of translations as well as Lorentz transformations. So Lorentz transformation is what's coded in the omega mu news. These are boosts when they involve time, and they rotation when they just involve length indices. And then the A news giving the A news giving the transformations. So this is on form 1 plus I is come a little there later. A nu, say P nu plus I over 2 omega let's say tau nu times m new or multiplied. Okay, so this is the general form that I would expect for a operator transformation. Yeah, definitely translations and rotations. And these guys, when I can identify what these are, will be the generators of the translations, and generators of the Lorentz transformations. Right. So if you've seen any bit about the algebras corresponding to Poincare transformation related to Lorentz, you would recognize these M's, for example. Right. So the point is that these guys, the P's and the M's, satisfy some algebra. Right. That algebra, the defined algebra, will be algebra corresponding to the associated Poincare. Okay. Our job will be to work out what that algebra is. We will find that there's actually an infinite number of different representations for the P's and the M's. We're going to work with one in particular, and this is a differential representation where we express these things as combination of derivatives and spectrum orders. They're not the only ones. I can come up with matrix representations. I can come up with integral representations. Okay. The point is that these representations are just a way of visualizing, writing this these generators, right? But all the representations will satisfy the same algebra. So our goal here is going to be to identify what these P's and the M's must be by comparing these two. Right. Once we have that, we'll have a representation for the generator of the algebra. Right. We will use that representation. I will do one of them for you, and I'll leave the rest as an exercise to determine what the algebra is. And once we know what the algebra is, any representation that you come up with for the generator of the algebra must satisfy those algebra. Okay, so that's the strategy. So by looking at this, I can read off that for these two experiments match, that P mu must be minus I d by dx mu d mu, and M mu must be minus I times x mu d mu plus I times x mu d mu. Okay. These two together, we're going to call it. Okay. This way of writing it furnishes what's called a differential representation for the generators. Lorentz in D, capital D dimensions and capital D equals then D plus 1. Right? And my notation was small letters because I'm writing Gothic for SO indicating the algebra. Right. So the point I want to make again, I want to emphasize is that this is one representation, one out of an infinite number of different representations that I could come up with, right? This one happens to be written in terms of differential operators. There are representations that I can write in terms of integral operators. There are representations that I can write in terms of matrices. Right? Whichever representation you can come up with, these guys must satisfy some algebra, some subset of commutation relations. You can see the three sets that matter here. P's with P's, the M's with the M's, and the P with the M's. Okay. Those three sets of commutation relations are the defining relations for the algebra that we're talking about. Okay. So let's work out using that representation. One set of commutations, and then I'll tell you the remaining set, and then part of the exercise sheet is to actually work it out with. Right. So I'm going to work out the most tedious of them, which is the m's to the m's. All right. Off with this computation relation of m mu with m, let's say, rho sigma. So this is going to be a commutator that I'm going to read off, and it involves derivative operators. So I need a test function. So I'll just take a test function of the x mu's. I don't really care about the indices in there because I'm only going to care about what the derivative operator does. And then I use this expression here to generate this of the Lorentz transformations in here. And I'm going to absorb some of the i's, but it'll be clear in the context of what it is we're doing. So that's x mu du minus x mu du. Operating on minus I x rho d sigma plus I x sigma d rho x. That's the term, and then I just drag it off. Minus I x rho d sigma plus I x sigma d rho. Sigma x mu d mu minus x mu g mu. All that. And the key observation of this is that because second derivative is mu, all second derivative terms in this expression will cancel out between these two terms. So the result is minus I eta mu rho x mu d sigma plus I eta mu sigma x mu d rho plus I eta mu rho x mu d sigma minus I eta mu sigma x mu d rho. This acting on this component x minus left from the first term, giving term and survive minus I eta sigma mu x rho d mu plus I eta sigma mu x rho d mu plus I eta rho mu x sigma d mu minus I eta rho mu x sigma d mu. Again, I'll back to the space one. It's not a particularly deep about this. It's going to go through the mechanics of working out the derivatives, canceling out the second derivative terms. However, now we can recognize n's in this expression. So by reorganizing this, we can read off that this is just eta mu rho m mu sigma minus eta mu sigma m mu rho minus eta mu rho and mu sigma plus eta mu sigma and mu rho. all acting on this arbitrary test function. Okay, this is what's called for any test function that has at least derivatives that are all fine. And we got then that if there are really ones, which is a commutator between mu and rho sigma. Just thinking in brackets is eta mu rho mu rho m mu sigma minus eta mu sigma m mu rho minus eta mu rho m mu sigma plus eta mu sigma m mu rho. Similarly, you can calculate that I mu nu with P rho, say, is eta nu rho dv minus eta mu rho dv. And finally, P's community amongst this stuff. Mu, zero. And these three commutators then constitute the Poincare algebra of the associated Poincare group. This is wait a minute. Find the d-dimensional algebra. Yes. One. You've probably already seen this algebra, you've probably already seen this derivation of the algebra, so hopefully you know what I'm saying is not new. What we want to do is exactly this method but applied to the conformal. But before that, let me just tell you how to get from the Poincare algebra to the Poincare to the elements of the Poincare group. So the definition of Poincare algebra associated to the Poincare group. Elements are B, say A and omega, and get A and omega by exponentiating these generators. So right, this e to the I a mu plus I 2 omega mu m mu. Okay. All right. So that's the Poincare algebra, Poincare group, and essentially things that you know already. Okay, from special relativity. What we want to do is apply the same thing to the conformal group. So recall that the conformal group is one definition of the conformal group is that it rescales the metric. So if you remember where we started off with this, Poincare transformation with approximation to the left of Minkowski metric in variables. So we went eta mu eta mu tilde and eta mu tilde was the same mu, but we had to make change coordinates. So we had eta mu dx tilde by dx tilde by dx, and that was equal to mu. For conformal transformation, we expect that eta mu on the right hand side will change by rescaling. Right? Something that we call omega, or actually some sort of positive, I think omega squared. Okay. So conformal transformations rescale the metric. I'm looking in that space here, but it's not too difficult to extend this to general curve space. Yeah, I think that is an exercise as well. Eta mu, so the defining property, and we have eta mu dx tilde mu by dx, let's say rho dx tilde mu by dx sigma is equal to omega squared, possibly a function of x, possibly some local rescaling. Omega squared beta rho sigma. So we want to follow the same strategy that we just used for the Poincare. So we want to take it from sensible approximations and write or infinitesimal. X cubed tilde x cubed plus delta x cubed, and we'll take omega as say 1 plus omega plus x. Okay. Now I take these and I plug it back into here. And follows that eta mu d by d x mu plus delta. So I want to write this delta x mu as, let's say, some beta mu. The sigma of x mu plus theta plus theta mu. Is just eta rho sigma plus the sigma theta rho plus d rho theta sigma plus terms that are or the sigmas orders in the square on the left hand side, as we did previously. And on the right hand side, we will find this is equal to eta rho sigma plus 2 omega beta rho sigma plus terms that are omega squared. I'm assuming that omega is small. Right, so if you lead order on both sides, we find that theta must satisfy the first order dependent equation. D sigma zeta rho plus d rho zeta sigma is equal to 2 omega beta sigma rho. So now we can subtract this heat. So I multiply both sides by another eta. Use the fact that eta mu is a diagonal identity. It's the chronic delta and d dimensions. If I count ones in g type, I'm going to get d. So that's on the left hand side. Left hand side, I'll get two terms. They both look like d rho zeta rho, d rho zeta rho. That's 2. And d rho zeta rho is just the inner product between the d operator and the zeta vector. For that notation, d dot sigma. That means d use g dot zeta. That means d u zeta mu. You don't confuse. So is it what is the more contracted indices and what's using? Okay. On the left hand side, I get this. So this is this. On the right hand side, I get a D. That's 2 D omega. In other words, omega is 1 over number of dimensions in space time times d dot zeta. Okay, and I can take this. Substitute back to greater than 6. And find that d sigma zeta rho plus d rho sigma is 2 over d dot zeta. This equation, let's call it 7, is called the conformal Killing equation. And it codes all the information that we want about generators of conformal symmetry in capital D dimensions. So equation 7 is sufficiently important that we give it its own name. Is called the conformal Killing it should be clear on the right hand side of this equation that capital D equals 2 is a little bit special. It's special because if I choose to work in two-dimensional space time, then this factor in front of the D dot sigma is just going to be 1. I don't have to worry about it. Okay. It's not particularly deep, I think. So D minus 2 there, I go D2, then the right hand side will be 0, then the homogeneous equation is solved. But it does tell us that the conformal symmetry on the plane is a hell of a lot simpler than in general D dimensions. So let's see if we can get some intuition for what's going on the plane. Let's see if I can get some intuition for what's going on in the plane. Sorry, for what's going on with this conformal Killing vector, conformal Killing equation, by studying transformations, conformal transformations in two space-time dimensions. Okay, so as a special case, note that D equals 2 is special. So, see why? Let's choose D equals 2 and solve this equation. That is what I want to do for the rest of this lecture. And then on Monday, we will talk about more general case of capital T space dimensions. Morals will go through unchanged, but the topic will become a little bit more tedious. All right. So let's take D equals 2. And in fact, let's simplify things a little bit further as well. So we take D equals 2 Euclidean dimensions. So really, I'm just looking at the two-dimensional plane on 2. So in two-dimensional Euclidean space, so R squared. Eta mu, the Minkowski metric, becomes just the chronic of delta. Delta mu, there's no change in signature, it's diagonal plus 1. So now let's take equation 7 and set mu and nu. Rho and sigma, and mu and nu, whatever, equal to 1. Okay, so in equation 7, we'll set rho and sigma. Suppose mu. Let's set, so mu and nu here are free indices. I get to choose whatever they want. There's an index contraction here that I don't get to choose. I have to sum over all of them. So what happens to mu and nu here? That's something. So I'm going to choose mu equal to nu equal to 1. Let's see what happens. On the left hand side, I get d1. That means d by dx1. Of zeta 1, the first component of zeta, plus d1 of zeta 1. Okay. You've chosen capital D equal to 2, so this factor cancels out. On the right hand side, I get d1 zeta 1 plus d2 zeta 2. Right. One of these guys will cancel out. This tells me that d1 of zeta 1 is equal to d2 of zeta 2. Probably see where I'm going with this. On the other hand, if we choose mu equal to 1 and mu equal to 2, then I'll get D1 of Z2 plus D2 of Z1 equal to D1 of Z1 plus D2 of Z2. I'm missing this again. All I did was substitute back to W as and then I can yeah, but I contracted getting equation 6 to read this off. And then I tell them what W but omega is, and then I substitute it back into equation 6. Pre-contract. Right. So that tells me the scaling equations, which makes sense because I've got units in the side and units. Okay. Now getting back to what I said there. So in R2, this eta becomes a delta, so 1, 1, that's just 1. But when mu is 1 and mu is 2, then this is actually 0. Which tells me that E1 of zeta2 is minus D2 of zeta1. Take that. So 38, 39. And together, any formal confirmation ordered the vector zeta must satisfy the Cartesian. So you'll remember what we did to solve the killing vector equation in the Poincare case. We converted it to a second order differential equation, then we were able to figure out the solution. Well, here we didn't even have to do that. We can, and then we get those parts where everyone knows that. But just in the first order form, the conformal killing equation reduces to the Cartesian, which means that any analytic solution zeta is going to be a conformal. This has tremendous repercussions. One is that I can immediately write down conformal transformations. And the other one, let me ask you, how many generators do you think this thing has? And remember, the number of generators is something about the dimension of the group. Right, so the Poincare case, the dimension of the group comes the number of generators, which comes the number of independent parameters that I need to specify some theta. There was a half d times d plus 1. Right, so capital D dimensions, dimension of the Lie algebra is a half d times d plus 1. What is the dimension of the conformal group? 2 dimensions. How many parameters do I need to give you to specify one of these functions? What is it? It says now. So if I ask questions like this, the answer will either be 0 or infinity. Maybe. Okay. Let's unpack it as we go. Right. So equations 8 and 9 are just the Cartesian equations for a holomorphic function theta of z equal to theta 1 plus I theta 2 with z to x1 plus I. So that means that, remember, what we're trying to do here is figure out what zetas constitute conformal transformations. Those are the zetas that satisfy the homogeniity equation, which is the same as the factorial equation. So any holomorphic function will do the job for me. Okay. So any there is a key. Okay. Right. And I can write down any holomorphic function because it's holomorphic. And write down a Laurent expansion, and the coefficients in that Laurent expansion are precisely the parameters that I just specified. Right? And the difference between the Laurent expansion and the Taylor expansion is that the series extends in both directions. Right? So this means that we can write down this function theta of z as some series expansion over n and z of some set of coefficients Cn z to the n. Okay, which means that there are an infinite number of parameters that specify such as that. Which generally means that the Lie algebra corresponding to the conformal group in 2 dimensions is actually infinitely infinite dimension. Okay. Which means that the formal the algebra in equals 2 is infinite dimension. Is there some intuition that we could use to understand why this is the case? The answer is yes. Because conformal transformations rescale the method. So there are coordinate transformations that I make that end up rescaling the method. So let's start off with the complex plane and write down the line element. So in C, the line element is dx squared, and dx squared is dz, z bar. And now let's make it conformal, any conformal. So the holomorphic coordinate transformation z bar to f of z f bar of z bar changes z bar to ef df bar, right? That's a new metric, a new coordinate system, and this thing is just df by dz, dx bar by dz bar, dz. So there's your rescaling measure. And any transformation Z to f of z will accomplish this for you. So that's why I think it's a huge symmetry group between that. And it's part of the reason why string theory formulated the string theory and worksheet is so powerful, because the symmetry group is so large.
And is the reason why we don't have a DFT? No.
Right, so holomorphic means that f can only be a function of z. Okay, very good. So next time we will extend this argument to general d dimensions, and we will write down the generators